Hello everyone and welcome that. Now that we have calculated the average distance for each of our clusters 1 to 10, we can plot the elbow curve using matplotlib. Let's do that. So plt.plot. Okay, let me give it some title. Let's plot the elbow curve. So plt.plot will pass clusters, which is 1 to 10, and then we'll pass our mean distance. And let's label our graph plt.x label, and we'll call it number of clusters, and we'll name our y label distance or average distance. plt.y label, we'll name it average distance. Let's also give a title for our plot by calling the title method on our matplotlib. So we'll call it elbow method for our k values. Okay, let me run it and show you what it looks like. So this is the elbow curve, and on the x-axis we have our number of clusters. From here are the number of clusters 1 to 10, right? And on the y-axis we have our average distance, and this is our elbow curve. And we can use this elbow curve to select specific k values for our clusters. So what this plot shows us is that the decrease in the average minimum distance of the observations from the cluster centroids for each of our clusters. And we see that as the average distance decreases, as the number of clusters increase, the average distance decreases, right? And since the goal of our cluster analysis is to minimize the distance between observations and their assigned clusters, so we want to choose the fewest numbers of clusters that provides us a low average distance. And what we look for in an elbow curve is a bend in our elbow, and that shows where the average distance value might be leveling off, such that adding more clusters will not decrease the average distance that much. Okay, so it's kind of subjective where we will choose. For instance, here we see a bend, one bend here when k value is 2, and then we have another bend here when k value is 3. Then we have our last bend, not that much, but I see a bit of bend here when k is equal to 6. So the main bends are when k is equal to 2 and k is equal to 3. So we'll consider those two bends mainly, and I'll also show you when number of clusters is 6 and compare our result to those two clusters. The bend appears when k value is 2 and when k value is 3. So which cluster shall we consider? And to help us figure out the solution, we'll deploy some more techniques. Just to summarize, we see that the average distance decreases as the number of clusters increases, and the goal of our cluster analysis is to minimize the distance between observations and their assigned clusters. So we want to choose the fewest number of clusters that provide a low average distance. And here there appears to be a bend when k is equal to 2 and k is equal to 3. And to help us figure out which of the cluster is the best, we'll further examine this cluster solutions when k is equal to 2 and k is equal to 3 to see whether they overlap or not. So for that matter, the first thing we will do is graph the clusters in a scatter plot to see if they overlap or not. But for our case, we are considering 11 clustering variables. So if we try to do a scatter plot, we are going to need 11 dimensions for our 11 clustering variables. And that will not be possible to visualize, right? Scatter plot will work to visualize just a few dimensions, but not 11 dimensions. For that reason, what we are going to do is use a method or analysis known as canonical discriminate analysis. Okay, canonical discriminate analysis. Okay. You can read more about it on Wikipedia, but I'll give you a brief description about canonical discriminate analysis. It's a data reduction technique which creates a smaller number of variables that are linear combinations of our 11 clustering variables in our case. Okay, and we'll create new variables which are called canonical variables, and they are ordered in terms of the proportion of the variance and the clustering variables, which is accounted for by each of those canonical variables. So the first canonical variable will count for the largest proportion of the variance, and the second canonical variable will account for the next largest proportion of variance, and it goes on like that. Okay, that's basically the method. And usually the majority of the variance in the clustering variables will be accounted for by the first two canonical variables, by the first two usually. And those are the variables that we can plot. And luckily for us in Python, there is a function known as PCA, and this PCA function will allow us to do this canonical discriminate analysis. So the first thing we'll do is import this function, and then we'll create an object that we will call PCA. That's the function name also. We'll just call this is the method name or the function name, and we'll create a variable and call this function name, and then we'll ask Python, by using this method or function, we'll ask Python to return the first two canonical variables, and then we'll create some matrix and include these two variables to estimate, which will be estimated by the canonical discriminate analysis. And after that, we'll plot those two canonical variables by assigning 3 cluster, and then we'll plot another one by assigning 2 cluster for our k values. Okay, so that's what we'll do in the next few minutes. Okay, let's go ahead and write the code and do some more explanation. So first, let's import PCA from scikit-learn. So from sklearn .decomposition import PCA, and we'll call the PCA method and pass 2. Usually, as I mentioned, we just need the first two canonical variables. Okay, and I'll save the method in a variable called PCA2 since we are using 2 canonical variables since we're calculating that. And as I mentioned earlier, we'll be deploying, as I mentioned before, we'll be deploying this for 3 clusters when k is equal to 3 and when k is equal to 2. So let's first see when k is equal to 3, right? Which is 3 clusters. Let's see the 3 cluster solution first. So we'll call our k-means model, we'll instantiate it, and then for number of clusters, we'll pass 3, and clusters, we'll pass 3, and we'll save our k-means model in a variable called, let's call it model1, and then we'll train our model by passing the training dataset, which is cluster train. So let's call the fit method on our k-means model for 3 number of clusters, and then simply pass cluster train. Okay, and those are the values that are used, the default values. Okay, back to our PCA method. So we have our PCA2, and then we'll call the fit transform method and pass our cluster train dataset. So I'll explain about this method once I write down the code. Okay, and I'll save this in a variable called plot columns, and then we'll do a scatter plot by calling matplotlib scatter method, and then we'll pass our x and y variables. So on our x-axis, we'll pass or use the first canonical variable, and for our y-axis, we'll pass or use the second canonical variable. So plot columns, and let's index this. This means the first canonical variable, and then for our y-axis we'll use the second canonical variable. Plot columns and then index 1. And for our C, we'll call our model's label function. So we have our k-means model 1, and then we'll simply call the labels method. Okay, and check out the scikit-learn documentation about this labels method. Next, let's label our x and y axis plt.x label. So for our x label, this is our canonical variable 1, and our y label will be canonical variable 2. Canonical variable 2 for our y-axis. And let's give it a title by calling the title method scatter plot for 3 clusters solution using 2 canonical variables. Okay, and we'll finally call the show method to show our figures, and let me call the figure method and pass the fig size attribute. Fig size we'll use 10 by 6. Okay, now let's discuss what we did here. So as I mentioned earlier, we can use the PCA function or method to do the canonical discriminate analysis. So the first thing we did is imported that function, and then we created an object that we called PCA2. So this PCA2 means we want to use 2 canonical variables. So this PCA2 asks Python to return the first 2 canonical variables. Then we created this matrix called plot columns, and this will include the 2 canonical variables, which is estimated by our canonical discriminate analysis. And then this PCA2 that fit asks Python to fit the canonical discriminate analysis that we specified with this PCA command or method, and the transform part of the method applies the canonical discriminate analysis to the cluster train dataset to calculate the canonical variables. Okay, that's what this line of code is doing in short. And then we call the scatter method to plot those 2 canonical variables by the cluster assignment. In this case, the value is 3 since we are doing 3 cluster solution. So this part, x is equal to plot columns, index colon, comma 0. It means plot the first canonical variable on our x-axis, and this part means plot the second canonical variable on the y-axis. And this model.labels method contains the cluster assignment variable from our 3 cluster solution. Okay, so that way when we plot and see our graph, we'll see 3 different color codes. Okay, so this tells Python to color code our points for each of the clusters. That way they will be visible. Okay, the 3 clusters will be visible. So that's what this method is. Okay, and then we have our labels, and finally plt.show. Let's run the cell, and there you go. You have your first canonical variable on the x-axis, second canonical variable on our y-axis, and here is our scatter plot for 3 cluster solution using 2 canonical variables. As you see here, we have 3 distinct clusters. One cluster is in green, another cluster in blue, and the third cluster is in red. As you see here, there is some overlap in here between the red and blue clusters. So some general observations from our scatter plot is that these 3 clusters are densely packed, meaning that the observations within the clusters are highly correlated with each other, and within each cluster the variance is relatively low, but there appears to be a good deal of overlap, meaning that it's not a good separation between these two clusters, the blue and red clusters, whereas the cluster in green shows a much better separation, but it's also at the same time it's kind of spread out, and this indicates less correlation among the observations. Okay, so that's some general observation about our 3-cluster solution. So with that observation, we'll go and check out the 2-cluster solution in the next lecture. Okay, and we'll also summarize and revisit this PCA and canonical variables. Thank you, everyone.